Hello everyone. So in this pre-lecture tutorial, I'm going to introduce the concept of limiting reactants. Up until now, the stoichiometry problems that we've been working in class have made the assumption that both of the reactants involved, or all of the reactants involved in a chemical reaction, are going to run out all at once, all at the same time. And so with that assumption, it simplifies the problem quite a bit. But there are those instances when a chemical reaction is occurring where the reactants don't both run out at the same time. I have more of one reactant than I do of another. And so that changes how we approach a stoichiometry problem. And so to sort of put this concept in context, let's actually begin by thinking about an everyday example where we have a limiting reactant or a limiting component to a process. So I want you guys to envision that I work in a bicycle store. And so it's my job to assemble the bicycle frames, which are on the left, and assemble them with the bicycle wheels, which I have here on the right. And let's assume that on a given day, I have 2 frames in the shop, but I happen to have 6 wheels in the shop as well. And so if I'm going to assemble a bike, each bicycle is constructed from 1 frame and 2 wheels. And based on the materials that I have, then I should be able to put together 2 bikes, right? Because then that would use up my 2 frames, but it would only use up 4 of my wheels. Okay, I'd have 2 wheels left over. Okay, and so I'll call your attention to 3 things here. First, notice that my process is limited in the sense that because I only have 2 frames in the shop, once I actually use up those 2 frames, the process has to stop. Even if I have more wheels, without frames, I can't continue to make bikes. And so because the frames actually limit my process, they can be considered the limiting component of this process. Now, because I have wheels left over, that means that the wheels are in excess. In other words, I have more of them than I need. And so because of that, I'm not going to be able to make 3 bikes because I'm missing a frame. I need to stop at making 4 bikes and then have some starting material left over. And in a nutshell, that's pretty much the concept of limiting reactants. So let's actually apply that to a chemical reaction and see how that works. So in this example reaction, I have 2 moles of sodium hydroxide that are going to react with 1 mole of carbon dioxide, and I end up with sodium carbonate and water. And I'm being asked which of these 2 reactants, the sodium hydroxide or the carbon dioxide, are the limiting reagent or the limiting reactant if I have these amounts of each of those reactants. I'm also asked in the subsequent part to tell how many moles of the sodium carbonate can be produced. Now, probably the most straightforward way to figure out which of these 2 reactants is the limiting reactant is to go ahead and calculate how much product I'm going to get with each of these amounts and see which amount of product is less, because that reagent that gives me the least product would then be my limiting reactant. So let's actually go ahead and do that. And I'm going to start with the 1.85 moles of the sodium hydroxide. So if you recall back to the beginning of the chapter when we were talking about mole-mole problems, I want to convert my moles of sodium hydroxide to moles of sodium carbonate. Okay, now I'm going to look to the balanced chemical equation to find my coefficients. And I have 2 moles of sodium hydroxide for every 1 mole of sodium carbonate. If I cancel my units, I'm already in moles of sodium carbonate like I want. And so what I'm going to do is I'm going to go and I'm going to take 1.85 and divide that by 2, and I end up with 0.925 moles of sodium carbonate. Okay? Now I'm going to repeat that same calculation, but instead I'm going to use my 1 mole of carbon dioxide. So I have 1 mole of carbon dioxide, okay, and I'm going to convert my moles of carbon dioxide to moles of sodium carbonate. Now, I'm going to look at the balanced chemical equation, and the coefficient for carbon dioxide is 1 understood. So it's 1 mole of carbon dioxide, and the coefficient for sodium carbonate is also 1 understood. So the mole ratio is 1 to 1. And so that would mean that I would get 1 mole of sodium carbonate from the 1 mole of carbon dioxide. Now I'm going to compare my 2 answers. And so what this means is, if I start with the 1.85 moles of sodium hydroxide, I'm going to get less product. That would mean that the sodium hydroxide is the limiting reagent. Okay? It means that once this 1.85 moles of sodium hydroxide is used up, the amount of sodium carbonate that I produce is going to stop at this value of 0.925 moles. Notice that I would get a little bit more product from the 1 mole of carbon dioxide. So that means that it is the excess reagent. Okay? I've added the sodium hydroxide and the carbon dioxide to this reaction mixture in such a way that the sodium hydroxide gets used up first and the reaction stops, having just created 0.925 moles of sodium carbonate. So that means that it's the limiting reagent, since I get the lesser amount of product from that amount of that reagent. And so now, by doing the problem in this way for part A, I've already answered the question for part B. It's asking how many moles of sodium carbonate can be produced. Well, as we've just discussed, because sodium hydroxide is my limiting reagent, then basically what's going to happen is the reaction will produce 0.925 moles of the sodium carbonate. Okay, with the carbon dioxide being the excess reagent. So go ahead and work on the follow-up assignment, working this type of problem. We'll continue to discuss this concept in class. Again, if there are any questions, then by all means email me, and have a good night.